हमें ये चाहिए कि लिमिट h goes to 0 ऑफ जो एक्सपेक्टेशन जिसकी हम ले रहे हैं वो 0 होनी चाहिए ना, लेकिन जब एक्सपेक्टेशन के अंदर वो चीज़ है जो हाउ कैन वी इम्प्लाई कि अगर एक्सपेक्टेशन ऑफ सम फंक्शन इज 0 एज h goes to 0 तो जो फंक्शन जिसके ऊपर एक्सपेक्टेशन अप्लाई कर रहे हैं उसकी भी 0 होगी।
हमारा claim nowhere differentiability is not general but in L2 omega sense.
तो सर L2 ओमेगा में डिफरेंशिएबल होने
So you have this differentiability with respect to the time. Okay, the differentiability is trouble, then you differentiate with respect to x. Okay, then you have weak derivatives and all that stuff. Okay, but with respect to time, yes, you can compute these increments. Okay. The covariance of Brownian motion at 2 times t is basically so you have to do this exercise 2.2, 2.4 and 2.3 from the book. Okay. Let's talk some more properties. Okay. Some more properties. So this chapter is all about talking about the various properties of the, Brownian motion. So it's all about Brownian motion. So we saw definition. Yeah, I just mentioned it that so in one of these exercises, so what does this exercise say? That if you see the reflection of the Brownian motion at okay, it's still a Brownian motion. But the reflection of Brownian motion is still a Brownian motion. If you scale a Brownian motion with a number, check that whether it should be a Brownian motion or not actually. Think you should be?
Yes.
It seems.
I think something would be. Because for Brownian motion, okay, check it up there. So for what choice of C it should be the Brownian motion. Okay, and if you see this, so 1 over C and W of say C square D, that's a Brownian motion. Okay. Which is really answering this question actually, that if you want to scale, you can multiply with only that number, which must appear here actually, because you can already see a trouble here. So if you compute the increment of this, so CWT minus CWS, so what should be its expectation of that is going to be 0, but the variance would be trouble.
C times D minus S.
C times D minus S.
It won't be.
It won't be. So we want variance to be T minus X. So it's not allowed C times D minus S actually. Okay. But if you do this, you will see the trick that this C square is there to basically cancel out. Okay. Anyway. So these exercises are interesting. Must go through the exercises. I way, why I'm writing it? Isn't that the covariance and the expectation of this WTWS must be same? I think it should be same. Why? Because what is the covariance of two random variables? So the covariance of two random variable is expectation of xy. The covariance of xy is expectation of xy minus expectation of x times
Expectation of y.
So if you have the covariance of WT and WS, this is already 0. And this is same actually. So okay, so these two are not two different things but same thing actually.
So this minimum, this you have given, is it interval or this two?
Then it's a minimum of the instant S and T actually.
But in the second equation you write.
No, yes, I T. I was thinking why I wrote them two separate things while they are the same thing. Anyway, these are the small things that you can see that. Let me define what do I mean by an abstract Gaussian process. And from a Gaussian process, a specific kind of Gaussian process, I would like to say that if you have a specific kind of a Gaussian process, it also becomes a Brownian motion actually. So abstract Gaussian process. So the process
Goes in there.
x of t, so it's a continuous time process. Okay. It's a continuous time process. So it's not takes the value at discrete time, but it takes the value at all times. Okay. So process is a Gaussian process. Okay. If for any choices of instants, choices of say times 0, t1 less than or equal to t2 less than or equal to tn. The vector increment, that's a vector. This random vector, x of t1 minus x of t0, yes, x of t2 minus x of t1, x of t3 minus x of t1, so on and so forth, t2, and finally x of n minus x of tn minus 1 is a Gaussian vector. Okay. So process is a Gaussian process. If you take any number of increments, say n increments, okay, and make a vector out of it, and that vector is a Gaussian vector. And by a Gaussian vector, I mean that it follows this, so it's an n-dimensional, it follows, so it has an n-dimensional normal distribution actually. Okay. Let me write it explicitly, what do you mean by a Gaussian vector actually. Okay. Let's see. Definition, an n-dimensional Zn, Z, that is a vector Z1, Z2, Zn, and I must say vector, and it's a random vector. is Gaussian with mean mu and covariance matrix sigma, the entries of sigma is the sigma ij, where I comma j can be anything between 1 to n. So sigma ij is the covariance of zi and zj. Okay. So if you compute, for example, the covariance of z1 with z2 and z1 with z3 and all that, then you make a matrix out of it. You call that matrix as covariance matrix. Okay. So make all possible pairs and compute the covariances, and make a matrix out of it. You call it a covariance matrix. Okay. Maybe a quick question: what would be at the diagonal of this covariance matrix?
Variances?
So it should be the variances, because if you compute the covariance of Z1, for example, with Z1, it's same as computing the variance of Z1. So it's going to be the variance of Z1. Okay. Let me write it. Sigma ij is the covariance of, more explicitly, expectation of zi minus its mu I. By the way, I must say that mu is a vector as well. Mu1, mu2, and mu n, where the mu1 is the mean of z1, and mu2 is the mean of z2, and so on and so forth. Zi minus mu I times zj minus mu j. Okay. So I have a random vector z in which, so it's n-dimensional random vector, but each of the entry of this random vector is a one-dimensional random variable. Okay, so if it is a one-dimensional random variable, it's going to have means, is going to have variances as well. Okay. Now, using n-dimensional, one-dimensional n random variables, one can create, say, an n-dimensional Gaussian vector with the variance mean and the covariance matrix sigma ij, or what would be the meaning of a vector, n-dimensional vector being Gaussian actually. So the meaning of it is that if it has density, which looks like this. F of x, okay. F that takes values from Rn and assign them a probability between 0 and 1, and f of x has this kind of an expression. So 2 pi n over 2 times determinant of the matrix sigma minus 1/2 times exponential of minus 1/2 x minus mu transpose times the inverse of the sigma matrix times x minus mu. Okay. You can see, you can also treat this as a definition of a vector that is following, or a random variable that is following the n-dimensional normal distribution. Okay. So So I'm going to say that Z is following an n-dimensional normal distribution, or it's a Gaussian if, its mean is this and covariance is this, and the probabilities can be computed through this PDF. So does it meet with our intuition? For example, take n to 1 actually. Okay, so think about it. Okay. So if you're going to get 1, so this is 1 over 2 pi, square root of 2 pi. This would be, so what is going to be the sigma in case of the 1? So it would be simply variance actually. Okay. Variance okay, na? Sigma would be only, because if you have a 1 actually, so about n equal to 1. So it would be simply variance. Okay. So what would be the determinant of that one number? Let's say the same number. Okay. And minus 1/2. So this will become what? So this is going to be 1 over square root of 2 pi sigma. Right? And what this is going to be? Exponential of x minus mu. Okay? So x minus mu transpose, but this is a one-dimensional matrix, so it's going to be simply x minus mu. Sigma inverse is going to be 1 over sigma times
A square हो जाएगा.
A square हो जाएगा. So this expression is precisely going to be what? E to the minus x minus mu square over 2 sigma. Sigma square.
सर ये 1 upon square root 2 pi कैसे आएगा?
कौन सा?
1 upon square root 2 pi.
ऊपर आएगा. So just take n equal to 1.
सर ऊपर होगा. न्यूमरेटर होगा ना कोई?
नहीं ये मेरे ख्याल से ये माइनस है इसके साथ. So you can see that when you take n, so it becomes simple normal density.
So sigma inverse something.
देखना. So I have a matrix, okay, that has only one entry, and I want to find another matrix, the inverse of it. So what should be the inverse of it actually? So it should be simply reciprocal.
So that we multiply when together it
You
should give
multiply that, you should get the one
identity.
To make more sense of it, experiment with n equal to 2 and see that what would be this formula when you have a bivariate normal distribution random variable. Okay, so bivariate normal distribution. Okay, so compute each of these things and see what you get. Okay, so at least you should have a concrete picture in your head that what does this mean. Okay. Even you can, with the abstract argumentation, we can show that this is a PDF. We can show it. It's not a big deal. Okay. Because think about it. This is nothing. This is just a number actually. That's a function of x. So it's going to be function of x, where x is what? X is a vector actually. Okay. So it's going to be a function depending on the components of the x. Okay. While this sigma inverse is like a constant, so it's a collection of the constants. So this is purely a function of x. So if you are in 2 dimension, for example, and you choose x to be xy, okay, then this expression is going to be what? Think about it. So it's going to be an expression in xy. That's a 2 by 2 matrix. That's an expression of x in xy. You multiply all them together, so this is an expression in xy. Okay, so ultimately this exponential is a function of xy, and this is just a number actually. This is the determinant. So a number is multiplied with a function of xy. So when you want to integrate it, you need to do the double integral actually. So if say you are in 2 dimension, and you can easily show that this is, it's not a big deal actually, that this is a PDF. Anyway, so why I introduced it? I introduced it because I I could define what you mean by a Gaussian process actually. So what do you mean by a Gaussian process? A Gaussian process is the process if you take a finite number of instants, okay, and n is not necessarily fixed. In other words, you take 2 instants or 10 instants or 12 instants or 200 instants for example, and consider a vector of their increments. Okay, their vector of their increments is going to follow an n-dimensional normal distribution actually. Okay, so if you are taking for example 10 increments, so it's going to be a 10-dimensional normally distributed. So it's going to follow a 10-dimensional normally distributed variable. So read it out. Read it out. It's not hard. It's just simple probability theory. I'll send you some illustrated, notes and exercises for it, so that you can get into it. But you can see that you already got some intuition. So why I define now this is one motion. Why I showed up? Because I would like to prove a small proposition. That goes like this. Now, for the previous case, take instance, for example, again, and define Zi to be the increment Wi plus 1 minus okay, this increment. Then what are some of the immediate things that I can say about this vector? First of all, what you can say about each of the Zi? So, they are normally distributed with mean 0 and
Ti plus 1 minus Ti.
Ti plus 1 minus Ti. So they are normally distributed with Ti plus 1 minus Ti. Okay.
For each of them.
That's each one of them actually. And by definition they are independent. Independent. So what you can say about the covariance of, for example, Zi, Zj? What should be the covariance of Zi, Zj?
Variance of
So this is Zi, Zj. So I have the, so in other words I have so that Zi, Zj. So Zi is the, so this is like the expectation of Wti plus 1 minus
WTI.
Brownian motion evaluated at Ti times Brownian motion evaluated at Tj plus 1 minus W Tj. Okay? This is what it is going to be. We need to subtract mean, but we know that that's 0, so there is no point of writing it. Assume that I is different from j. Then do I know something about these two things? Look at the definition again.
independent.
So they are independent actually. So the expectation of two independent random variables is what?
the expectation of each
Product
different
of expectation.
product of expectation.
Product of expectation. But I know that the expectation of each, so expectation of this product is the expectation of this multiplied by the expectation of this. So what is this?
Okay.
0, total 0.
Okay. So the expectation of the product of increment should be the expectation, since they are independent, the expectation of this increment multiplied by the expectation of this increment.
Yes.
So do I know about the expectation of this increment?
It's 1
0.
0. This must be 0. Okay? What would be the case when I is j? So there are two possibilities actually. Okay? So what would be the
It will be the variance of Z.
It's going to be variance of, so because if the I is j, then this covariance of Zi becomes basically variance of Zi, so this is equal to Ti plus 1 minus T. Okay? So can I say something interesting about sigma?
Diagonal matrix.
So it's going to be a diagonal matrix, okay, in which this is T2 minus T1,
T3 minus
T3 minus T2, and so on and so forth, Tn minus
Tn minus
Tn minus 1 and entire
0.
of rest is 0. Okay? And what would be the inverse of it?
Just
1 upon
equivalently
G.
So
inverse
just
of
inverse the product actually. Okay. So the question, can I talk about the distribution of, this vector, joint distribution of this vector actually. Okay. Would that be normally distributed? Would that be normally distributed? They are individually normal. I can't say it unless I know that this is a Gaussian process actually. Unless I assume that, this vector is a Gaussian random vector actually. Because, you can have a situation where you have two normally distributed random variables, but their joint is not necessarily normal actually. It's something else. Okay. So you have to be very careful. So here's a proposition. So the key proposition, in other words, when a Gaussian process is going to become a linear process. That's what the question that it answers. So proposition is this, that if x is, okay, if x equal to x of t, t bigger than or equal to 0, is a Gaussian process. We know what is the meaning of Gaussian process. That take any number of increments and make a vector out of it is going to follow the n-dimensional. And it doesn't say, so this is an important point to make sense of it. It doesn't say that you always take the n increments actually. You can take any number of increments actually. The definition of Gaussian process is take any number of increments, any number of instants, and consider any number of increments. You can take 2 or 3 or 10 or 15 or 100 instants actually, and consider their increments. So if you are taking 3 instants, you're going to have a, for example, 2 increments, say 3 increments. So all 3 increments is going to be a random Gaussian vector in this sense. Okay. If you are taking 10, it's going to be a Gaussian random vector. So if x of t is a Gaussian process, okay, and x starts from 0, okay, and has almost surely and has constant expectation. Expectation. In other words, brackets, that is expectation of x is a fixed vector mu. Okay? Constant expectation. Almost surely continuous paths. And covariance of x of x and x of t is minimum